Alright guys, let's go ahead and work on those notes for 8-4. Alright, so let me remind you a couple of things first. We've been talking about simple interest. And simple interest uses one of these formulas. These are the same formula, remember. One has the P pulled out and one has the P distributed through. But they are the same formula, and that is only when we're using simple interest. Simple interest means that the interest is only compounded on the principal of the loan. It is not anything other than that, and it's not the world that we live in. The world that we live in is definitely a compound interest world. So I told you last week that simple interest may exist at best in pawn shops or with loan sharks, but it's not really something that's that applicable today. So why did we do it? We did it because I wanted you to see where compound interest comes from. It is based on simple interest. It is just that we're compounding it every month, not every year, not once in the life of the loan, just more often. It's compounded more often, which makes the interest pile up. So look at this example. So this is a pretty neat little example, and I've heard a few different versions of it, but they're all basically the same. So Manhattan Island, New York, was bought from the Indians for $24 back in 1626. So that was probably a reasonable amount back in 1626, even though it sounds really small. And so it's been suggested that they had put that money in the bank, 5% interest rate, which is not all that high, but a pretty good interest rate, and it was compounded monthly. By the year 2010, they would have over $5 billion in the account. And I think this scenario is fantastic. It's showing the difference between simple interest and compound interest. So let's just walk through it. So we've got a time frame, if we stop at 2010, so that's 10 years ago, of 384 years. All right, so let's do simple interest first. All right, so we've got the principal, which was $24. We've got the interest rate as a decimal. Remember, that's 0.05 times the number of years. So that is 384 years. So let's just pop that into the calculator and see if we end up with over $5 billion. I don't know if you have your calculators out. So I will just go ahead and do that calculation. Times 0.05. Okay, so if you pop that in the calculator, you come up with a great sum of $484.80. So that's a far cry from the $5 billion that was claimed. So is the book accurate? Well, maybe it is, because what did it say? It didn't say anything about simple interest. As a matter of fact, it had a key word in there, and that key word is compounded. Well, how often is it compounded? It's compounded monthly. So that means it's earning interest not once a year, but 12 times a year. So that means that not only are they earning interest on the original $24, but every time they earn a little bit more money, they also earn interest on the previously earned interest. That's not odd to say, but that's what's happening. So let's go ahead and throw that in there. Compounded monthly. Now, monthly is typically what you would expect. You pay credit cards monthly. You pay car payments monthly. You pay mortgages monthly. If you deposit money into a CD, you earn interest monthly. If you have a savings account, rates are really low right now, so you're not earning much interest, but you're earning a penny or two, and you're earning those monthly. So when we make investments, they usually pay us back monthly. Not 100%, but very often. So compounded monthly. We earn interest each month. Okay, so we're earning interest every single month. So watch this. I'm going to show you why we did the simple interest formula. So go back to simple interest. All right, so the future value, the starting value, the rate as a decimal, the time in years. So look at this. So this is when the Indians first started. So they started with $24. So they would put that into the simple interest formula. Here it is. And remember, we need the time to be in terms of a year. So since it's just going to be for a month, we're going to put 1/12 as our time. So when we plug that in, we find out that the end of that very first month, they had $24.10. So the next month doesn't start at $24. It starts at $24.10. And then that's going to be my new P. Now right now our amounts are tiny, but they're going to grow, right? So for a little while it only goes up by a dime each month. But then the next month, that's the new starting amount. And so they get to earn interest on the interest that they've already earned. You've heard people say you've got to have money to make money. Well, this is it. You can live off interest if you've got enough money in the bank. Now, it's going to require a little bit more than $24 unless you go out a lot of time. So every single month, that simple interest formula is coming into play. And eventually, it's going to jump up and it's going to be more than a dime that we're earning. I'm not sure if it is after that point or not. But it just keeps getting higher and higher and higher. Now we're talking 384 years. So we have got some significant interest buildup at the end of that. So we're compounding every single month. So in 384 years, that is 4,608 months. So that means that we would have to do this. So far we've done it, what, 1, 2, 3, 4 times? So we only have 4,604 more times to go to figure out how much money they would have if it was compounded monthly. I know we're on break, but I don't have that much time. So not to commit to doing this. So what we need is we need to get away from the simple interest formula, and we need some fabulous mathematician to come up with a compound interest formula so we can finish our Netflix binge. So here's the new formula, the one that's going to take care of that for us. All right. Future value, beginning value, rate as a decimal, how many times it's compounded in 1 year, how many times it's compounded in 1 year, times the time in years. Those are exponents. So you've got this number twice. That's how many times it's compounded in a year. So now it could be 1. If it's compounded annually, then your n in both places, it's always going to match. If it's compounded annually, that's just 1 time for the n. Semi-annually, that's 2. Quarterly, that's 4 times a year. And then the most common, monthly. Now I know daily is 365. My math lab is going to tell you if it's daily to use 360. That's considered banker's daily. I don't know why they come up with 360 because we all know there's more than 5 bank holidays in a year. But 360 it is, and they will remind you. Now, the only thing different you're going to see with the word compounding is continuously. And if you see compounding continuously, you use a different formula. You use what I call PERT. But it's your future, future value equals starting value, E. This is the E on your calculator. E is like pi. You know how pi is 3.14? E is 2.718, and it goes on forever. It is a key on your calculator. If you look on the left-hand side, it's either going to be on its own button or it's going to be the second function to the button that says natural log. ln. Okay, and then that's going to be raised to the RT, rate times time. All right, and that is something that you use when you see the word continuously. And we'll practice that here in a moment. All right, so for right now, I'm going to end this video with me plugging in these values, compounding monthly. All right, so for compounding monthly, n equals 12. All right, so we don't know the ending amount. We're hoping it's going to be over 5 billion. All right, compounded monthly, so put in the 12. And that's going to be for 384 years. So when you punch that in your calculator, you can punch that in all at one time. Most of you have calculators where you can follow suit. Make sure that that exponent is 12 times the 384. All right, give me a second. Let me punch it in. All right, here's my number. 5,027,378,918.03. So that is definitely over $5 billion. So that is a huge difference. So remember, if we compounded it using simple interest, $484.80. Compounded monthly, over 5 billion. All right, if you do have trouble getting this in your calculator, use order of operations. You can say 0.05 divided by 12, then add the 1, then raise it to the 12 times 384, and then times the 24. That's just following order of operations. I really think you can probably put it in your calculators just like it looks. Most of you have the gray and white calculators, the graphing calculators, or something comparable. Let me know if you struggle. All right, so that's going to end this video, and I'll pick up on the next page, and we'll finish out this section with some practice problems.